Great, thank you. I'm gonna start sharing my screen. Can everyone see my screen right now?
Yes.
All right, awesome. So for question 1, we have a helical wheel of a alpha helix structure, and we know that the N-terminal end is below the plane of the page, and then the C-terminal end is above the plane of the page. And we also know that to the right of the alpha helix, we have a negatively charged lipid bilayer. So we got some negative charge here. And then to the left, we have water. And the two building blocks we have are glutamate and arginine. So can someone tell me which amino acid are we going to put on the left or on the right in terms of their polarity or charges? Feel free to unmute yourself. All right. Anyways, I can't see the chat, so maybe somebody have put the answer there, but we're gonna put arginine on the right because it is positively charged, and we have a negative charge also on the right, and that's gonna attract the arginine. So it's good to put arginine here, and glutamate on the left. So in order to fill out a helical wheel, we need to figure out two things. One is how far away is between two residues, and the directionality of the helical wheel, in that whether it's clockwise or counterclockwise. Let's first work on the distance. So we know that a monomeric alpha helix have 3.6 residues per turn. And then 360 degrees, which is around, divided by 3.6, give us 100 degree per residue. And since that our circle is divided into 18 equal sectors, we know that each sector is 20 degree per sector. Therefore, because 100 degree divided by 20 degree is 5, we know that the distance between two residues is going to be 5 sectors. That gives us the distance between residue 1 and residue 2. Now we need to figure out the direction of the helical wheel, whether it's going clockwise or counterclockwise. So a clue to this is we know that when a peptide is being formed or synthesized, new amino acids are always added to the C-terminal. So an easy way to figure out the directionality of the helical wheel is to have your right hand ready, and then have your right thumb pointing toward the C-terminal. And then curl your other 4 fingers. That is going to give you the direction of the helical wheel. So if you have this picture on the left, and if you look from the top to the bottom, and then the C-terminal is on top, if you have your thumb pointing upward or pointing out of the page to the C-terminal, and then curl your other 4 fingers from I+1 to I+2, this is going to give you a counterclockwise direction, because new amino acids are being put onto the C-terminal when a peptide is being synthesized. And then also, for the picture on the right, when the C-terminal is at the bottom, you also have your right thumb pointing toward the C-terminal, which in this case is into the plane of the page and then curl your fingers, you'll see that this direction from I+1 to I+2 is in a clockwise direction. So this is an easy trick to figure out the direction of the helical wheel. And in our case, we have the C terminal end above the plane of the page. So we have our right thumb pointing above the plane of the page, and then curl your fingers. You'll see that this is going to go a counterclockwise direction. And since we already know that it's going to be 5 sectors per residue, we know that our second residue is going to be 1, 2, 3, 4, 5. Yes, it's going to be here. And it is also going to be R because it's still on the right side and it's interacting with a negative charge. Then our number 3 residue, I think, is going to be here. And just basically keep going until you hit 10. I think there's a total of 10 residues in this case. Are there any questions for 1A? Right, if not, I'm gonna go to 1B. For 1B, we have a coil structure. And it says, for question 1B1, it's asking us, why is this circle only divided into 7 sectors as opposed to 18 sectors in the helical wheel in part A? Provide a convincing reason for this. So a coiled structure is a dimeric structure formed by 2 alpha helixes to achieve better stabilization through the hydrophobic interaction at the interfaces between the 2 helixes. So for A and D, for residues AA and DD from the 2 alpha helix, they're going to have hydrophobic interaction. And then because they are going to form the hydrophobic core of the structure. And residues E and G. So between GE, you're going to usually have ionic interactions, or so you're going to have like charged residues on a G and E residue. So between DD and AA, you have hydrophobic interaction, and between GE, you have ionic interaction. So that's some basic information about coiled structure. To answer 1BI, you should know that to achieve better stabilization, the coiled structure is going to have 3.5 residues per turn instead of having 3.6 residues like a regular alpha helix is going to have. So the benefit of having 3.5 residues per turn is that it gives you a pattern that repeats every 7 residue. So every 7 residue, this is per 2 turn of the helical wheel. So it's also asking us, what is the rotation around the circle per residue in a coiled coil? So we know that there's 3.5 residues per turn. That's going to give us approximately 102.85 per residue. Oops. And since we have 7 sectors in this case, we know that each sector is about 51.42 per sector. And then since the rotation per residue is 102.85, you divide that by 51.42. And that's going to give you 2 sector per residue. So that answers question 1b, I, and then it also tells us the distance between two residues in this helical wheel. So for the second question in 1b, a peptide containing only the residue serine, isoleucine, aspartate, and lysine forms a dimeric coiled in the water, but the coil is not stable when salt is added. And it tells us there's no hydrophobic residues are solvent exposed, and then the direction of the helix is the same as before, which is counterclockwise. So let's draw this. Since we've already figured out the distance between two residues is going to be 2 sectors, we can just directly start drawing it. E, then we know this is F. And goes to is G. And that's our last residue. So we want to go backwards from E. So the letter before E would be D. And the letter before D is C, and the letter before C is B and A. So, since we know that at the A and D position, we need them to form hydrophobic interaction to stabilize the coil, we need to put a nonpolar residues at the position A and D. And then at position G and E, we need to put something that can form ionic interaction. And since lysine, we already have lysine at position E, and we wanted to form a ionic interaction with the G residue of the other alpha helix. So we want to put something that is negatively charged at the G position. And on position C and F and B, which are solvent exposed, we want something that is polar. Because in the question it says there's no hydrophobic residue or solvent exposed. So that should give you enough information to answer this question. Are there any questions regarding this helical wheel?
I have a question. This is kind of about part A and kind of also part B. So when we say we need a polar residue to interact with water, I guess, couldn't it also be charged, or does it have to be neutral?
I think neutral will be better in this case.
Why is that?
Because I'm not entirely sure, but my understanding is if you have other charge outside, it might form other unintended interaction. But I would guess if in this case particularly, I would think if you put a negatively charged on C and F and B, it might also work, as long as it's nonpolar. It should be fine.
Okay.
Yeah, but to be complete safe, you can put something that's polar and not charged. That is the safest choice.
Okay.
Yeah, but I would assume if there's a negatively charged residue on C and F and B, it should also be fine.
Okay. And for sorry, to go back to part A. So since glutamate is negative and arginine is positive, we don't have any neutral polar residues.
Yeah.
How do we
for
choose?
question 1, you just put the positively charged amino acid on the left, because there's a negative charge lipid bilayer, and then on the left you would put the glutamate.
Okay. I guess I don't quite understand why it has to be glutamate on the water side.
From my understanding is, so you have water, right?
Mm-hmm.
Oh, H. And water, it has partially negative charge. So you want something that is slightly positive to, form a better interaction with water, in which the oxygen is very electronegative and is has a slightly partial negative charge. So a positive amino acid on the left interacting with the partially negative charge.
Let me just I just want to interrupt you. You've given a beautiful presentation, but water is neutral because the negative charge on the oxygen is balanced by positive charge on hydrogen. So what's the question?
My question, I'm just not sure how to determine which amino acids should go on the same side as water, because we have two options. One is positively charged and one is negatively charged. And I don't know how to figure out which.
They would both go on the side of water, so I don't.
So there's no one specific right answer. There are multiple.
Yeah, with water is not going to select residues.
Okay.
It's only the other interface that's going to select residues.
Okay, that makes sense. Thank you. Sorry to take up so much time.
Thank you. And for the no worries. Are there any more questions? If not, I'm gonna go to the last part of the question. Explain why the addition of salt destabilizes the quote coil. So since we already talked about that, between amino acid residues G and E, we have ionic interaction. So if you put salt into it, such as sodium chloride, you're basically putting a bunch of cations and anions, which are gonna compete with the G and E residues to form ionic interaction between them, which is gonna destabilize the ionic interaction between residue G and E. So that's gonna destabilize the quote coil in return. That's pretty much it for question 1. Are there any questions? Or if not, if there are any more questions, feel free to put it in the chat. I'm gonna stop sharing my screen now.
All right, hey everyone. I hope you're all doing well. I'll be presenting question 2. All right. And then if there's any questions, I'll have the chat open so I could see that. So part A, So part A is asking, there's 2 monomers over here forming a dimer through this aspartate-aspartate interaction. And then part 1 is asking, how many residues does each protein contain? So we're just looking at 1 monomer over here. So let's see what we know so far. So each protein consists of 2 transmembrane alpha helices, which is there's 1 here and then 1 here. There's 1 N-terminal loop, 1 C-terminal loop, and then there's a linker loop between the 2 alpha helices. And then we're also given that the membrane is 35 angstroms thick and that each loop is 5 residues long. So what we could do is we could fill some things out. So the rise of the alpha helix we know is 35 angstroms. And then in lecture, you learn that the rise per residue in an alpha helix is 1.5 angstroms. So if we divide these 2 numbers, we could find the number of residues in the membrane. So, I mean, per alpha helix. So 35 angstroms divided by 1.5 angstroms per residue. And then that gives us 23.3 residues. And then just round that up to 24. But keep in mind that this is for 1 alpha helix, so that's just for this part, and it doesn't account for that, so you want to double it. And then the total amount of residues would be 2 times the residues in the alpha portion, plus the N loop portion, C loop portion, and linker loop portion. And then you have the values to plug in, so just plug that in and you'll be able to see how many residues each protein contains. And then this part is asking about this asp-asp interaction. So it's asking what happens to the pKa values of aspartate in this protein. So normally aspartate has a negative charge to it. And then if aspartate interacts with aspartate, that'll lead to repulsion, which is very unfavorable. So how do we make this interaction favorable? And that could be done through hydrogen bonding. So normally aspartate looks like this. But then if we want to participate in hydrogen bonding, we could do that by gaining a proton. And now it'll look like this. So in order for this to be true, the pKa needs to shift some way. So if pKa increases, that means that the amino acid becomes more basic. So higher pKa, think more basic. And then if something is basic, that means it's more likely to keep a proton or take a proton away. So you're going to gain a proton. And then if pKa decreases, your amino acid will become acidic. So low pKa equals acidic. And then if something's acidic, it'll lose a proton. So we're in the realm where we want to gain a proton, like we said over here. So yeah, pKa of aspartate will increase. And then the next part is asking you to draw the interaction of the hydrogen bonds. So we know that the partial charge on H would be positive, and then this one have a negative charge, positive and negative. And then what we could do is align them so they could form hydrogen bonds. Like that. And then you'll have hydrogen bonds here and here. So now moving on to part B. This is asking about ridges into grooves interactions. And one thing to keep in mind is that alpha helices could either have an I plus 4 interaction where the angle is 25 degrees, or they could have an I plus 3 alignment where the angle is 45 degrees. And it's asking you, if the angle between two alpha helices is 90 degrees, what is the nature of this interaction? Is it I plus 4, I plus 4, I plus 4, I plus 3, or I plus 3, I plus 3? So it's relevant to know what the goal of packing alpha helices is, and that is to align ridges and grooves so they could basically lock together. So let's go through an example to make that more clear. So we have helix 1 and helix 2. These are the ridges, and then the things between the ridges are grooves. And then what we basically want to do is we want the ridges of 2, so these, to pack in between the grooves of helix 1. So what we're going to do first is rotate helix 2 180 degrees. So that will look like this. And then you see that these ridges are crossing, and we don't want that. We want them to be parallel. So we rotate this by a certain amount, and then they will ultimately be aligned. So now they're parallel. And the angle between them would be the sum of the angles of this interaction before. So this ultimate angle is theta 1 plus theta 2. And then knowing that, you'll be able to determine which of these three choices are correct, because we know that the angle between the helices is 90 degrees. And then for part B, it just says to justify your answer with the drawing. So let's say there's helix 1 here and helix 2, helix 1 and 2. We want to rotate helix 2 180 degrees, so that's this. And then we want to place it on top of helix 1. And then we align it. So we move theta plus theta, and then that will give us our alignment. And yeah, that's it for part 2.
All right, let me share my screen so I can go over part 3. Cool, can everyone see my screen?
Yes.
Okay, cool, thank you, whoever that was. All right, so part 3, let me just pull up my notes real quick. All right, got it. So we can start with part 1. It's basically asking us to draw the side chains of glutamine or asparagine in like or specifically asparagine in a 3 amino acid kind of array. So we can just start by drawing out one. It goes like that carbonyl, then you have your amine group right there. And we can see this is very similar to question 2, which we just went over, but we can see that, you know, there's a donor here and an acceptor here. So we can just copy that and paste it and line it up so that there's hydrogen bonding. Cool. And then the question asks for 3, so we can just paste another one and line that up too. Cool. That's something like what your answer for question 1 should look like. All right, question 2 takes us back up to this figure right here. And it wants us to fill out this sequence. And there's 2 of these, and we want to know, you know, are they parallel or anti-parallels? So kind of one way to do this is, I'm going to zoom right in here. So if it was parallel, it would look like this, QQ. And then the hydrogen bonding would be, or I guess the bonding would be, interactions would be between the stuff that's lined up. So like this I would match with this I, this N with this N, and so on and so forth. And then conversely, if it's not parallel, it's anti-parallel, it would be I, Q, here, Q, and I. It would be something like that. And then whatever is stacked is basically interacting here. And we can see that in this configuration, you have this NQ and then this QN. That's kind of somewhat unfavorable relative to the parallel configuration. So because of that, we can recognize that the parallel, I guess, arrangement is more favorable. So we can fill that in. And Q, I, Q, Q, and I. And then you can figure out, or you can fill in the other one. And then obviously the top plane would interact with the top, and the bottom or below the plane would interact with the side chains below the plane. So it would look something like that, the interactions with this I here, this N here, Q, and I, and then so on and so forth for this question. All right, so for question 3, we're basically given virtually the same sequence, except for this Q right here is swapped out with a D. And we know that, sorry, we know that D is negatively charged at certain pHs, but not all pHs. So, we have 2, we have this Q going to AD, and then we have a pH 7 and then a pH of 4. 2 possible pHs that we're assessing this question at. So at pH 7, it is charged, it's negatively charged. And at pH 4, we know that it is neutral, and this is just based off the pKa value of the side chain. And the question is whether like they would form fibrils at pH 7 or at pH 4. And we know that if something is charged, that it can electrostatically repel, which means that it would be much less likely to clump up. So you can imagine you'd have like your thingy, and then there's a negative charge here that would repel this, pushing it and stopping it from clumping. Whereas if I took the same thing and remove the negative charge, these can actually like pull in and lead to like a more clumping like that. That's a very crude drawing, but that's basically what's going on there. So based on that, we know that they will form at pH 7. So that's yes. And then at pH 4, they will not form. And yeah, that's it for question 3. I know that was a little bit fast, but I'll be in the chat if there's any questions.
All right, I'll be going over question 4 now. Let me just make sure this is showing my clipboard. All right. All right, you should be seeing my clipboard now. All right, so for question 4, we will be going over the basics of the Ramachandran diagram again. And here I'll just draw a quick peptide backbone. Okay. So you have this peptide backbone, and then the three distinct angles that you'll have are here, here, and here. This first one here will be phi. Second will be psi. And the third one will be omega, which is. And then, oh, they don't ask you for omega, but remember that omega is usually constrained between being either 0 degrees or 180 degrees because of the resonance between the double bond here and this N and this CN bond. But the other two are the phi here and the psi here. For part 2, you're asked to basically sketch the Ramachandran diagram, and this can be found in your lecture. So I'll just quickly reproduce it here. There should be a region here with alpha. There should be some region here with beta. And there should be some region here with the left-handed helix. All right. So to give you some physical intuition behind why this alpha is like slightly a small negative angle and a small negative angle, I'll show you this diagram. So here, imagine you have basically a peptide backbone that is cis, so which is 0 degrees. So you'll have C here with the R coming out, and then since it's cis, you'll have some kind of R prime where R prime is the rest of the backbone up here. Okay, and then so you can see here that this does not follow the alpha helix because it is cis, and this comes up. And if you continue with this pattern, you'll either come back around and hit and have some steric interactions with the C, this N, or the side chains will interact somehow inside of this R prime. But to follow this alpha helix here, you want to bend this R prime down, a negative angle. So you'll have an N, and then you'll have a C with an R with the residue, and then this will now be bent back to here, R prime. And if you continue doing that for the next angle, which is the psi angle, the next one will bend to here, and then it'll bend back to here, and then it'll bend here. And you'll have that nice alpha helix where all the hydrogen bonds are satisfied, lined up, and all the R prime or all the residues are facing out of the helix, so they're not they don't have any chance to sterically interact and be energetically unfavorable. And that is why you have the alpha at a small negative angle and a small negative angle. And then you can see a similar thing with the beta if you would like to draw it out, and the left-hand helix is the inverse of the alpha, so it would be a small positive and small positive. So that is for question 2. For question 3, they're asking you about, well, you have a scientist that sees a biologist that is looking, that has a Ramachandran diagram that has a lot of things in the disallowed region. And we're wondering if he's made a mistake or if this is realistic. Now, remembering what the forces are that actually determine where the proteins can be and what the allowed angles can be, you can remember that these are actually van der Waals forces, and specifically van der Waals repulsion force. Okay, and if you remember the graph of the van der Waals forces, you remember that you have this very exponential area right here, and then this end curve, and this is where you'll have them in van der Waals radius, that close contact, and inside of that is when you'll have them intersecting each other. Now, looking at this diagram, you should be able to see that the van der Waals repulsion has a great increase in energy, and you should be able to relate this to the energy that you'll get from heat. And you should be able to see why this repulsion is why you cannot overcome this repulsion with heat, and why the scientist is not correct in saying that the specific properties of the protein under heat are allowing traditionally disallowed regions of the van der Waals forces. I'm sorry, of the Ramachandran diagram. And that should be all for question 4.
All right, I'm going to start sharing my screen. I'll be doing question 5. Okay, can everyone see the screen?
Yeah.
Okay, awesome. So question 5 is asking, so the diagram below shows an amphipathic beta strand with 8 amino acid residues. One side of the strand faces the lipid bilayer, and the side chains are inserted into the membrane. This will be only hydrophobic side chains on this side. And then the other side will be exposed to water with only polar or charged side chains found on that side. And this diagram only shows the carbon alpha atoms, and no hydrogen atoms or double bonds are shown, and heteroatoms may be included, but they're not identified. So just important things to know, like when starting this problem, you should try and kind of like, what's the important information to take away? So one thing, it's amphipathic, and so there's going to have both hydrophilic and hydrophobic portions. One side is facing the lipid bilayer, so that'll have only hydrophobic side chains as stated. And the other side is exposed to water, and that will have only polar and charged side chains. And then also just important to remember that there can be nitrogens, oxygens, or sulfurs. So you don't want to confuse like everything to be a carbon. And so the first question is asking which side of the strand, the upper or lower side, faces the membrane, and to justify that answer. So this question basically is asking, we know which side, we know that the side that's going to be facing the membrane contains only hydrophobic proteins. And so this question is asking which side is definitely containing hydrophobic proteins. And so in order to answer that, I would suggest starting by looking at like the individual amino acids and trying to figure out what they could be. So for first, I looked at amino acid 1 and amino acid 3, and from their structures, I can tell that they're either valine or threonine, but you can't decipher which. Then for amino acid 2, it looks like it's arginine. 4 looks like it's either going to be glutamic acid or glutamine. 5 and 7 both look like they're going to be methionine. And 6 looks like it's either going to be leucine, aspartic acid, or asparagine. And 8 looks like it's going to be histidine. So now you need to figure out which amino acids are polar. And so to do this, you should look at an amino acid for which there's only one option. So amino acid 2 or 8, or the amino acid 5 and 7, you can look at these and figure out which ones are polar and which ones are non-polar. And then the information will all like work together, and you'll be able to figure out pretty easily which side is going to be facing the membrane from that, just by which side has the non-polar versus polar. And so then for the second part of the question, it's saying based on the information provided so far, only 2 of the residues cannot be identified unambiguously. So for these 2 residues, state the residue number and state the possible amino acids. So even though it seemed like there were a lot of kind of ambiguous amino acids, once you determine which face is polar, you can now narrow down some of the other possibilities for each amino acid. I'll just give you an example. So if we determined, I'm not saying this is correct, but like if you determined that, for example, the top face of the membrane was polar, then you could be sure that amino acid 1 and 3 were both threonine, because it states in the problem that all of the amino acids facing the water will be polar or charged. And so vice versa, if we determine that the top face of the membrane was nonpolar, then we could be sure that amino acid 1 or 3 was valine. And so do this for all of the amino acids, or as many as you can. And you'll find that there are 2 that you can't do this for, that knowing which side is hydrophobic and which side is hydrophilic still doesn't allow you to narrow it down to just 1. And so those will be the unambiguous amino acids. And so this would likely happen if you had 2 possible amino acids that one could be, and they were both polar, or 2 possible amino acids that it could be, and they were both nonpolar. And then for question 3, it's asking what's the identity of residue number 3, and give the 3-letter and single-letter codes and explain why there's no ambiguity. So earlier we narrowed down the possibilities for 1 and 3 to be valine or threonine. And so this is valine, which is hydrophobic, and then this threonine, which is hydrophilic. So knowing this information, and since you've already at this point determined which side of the membrane is hydrophilic and which side is hydrophobic, or which side of the amino acid is hydrophilic and which is hydrophobic, you should pretty easily be able to determine which these are. And then the next portion of the question is saying that the 2 residues that are adjacent to each other on the same side of this strand are considered to form an ion pair if they're oppositely charged. For example, if 4 and 6 are oppositely charged, they will count as 1 ion pair. And at pH equals 6, the peptide will have 1 ion pair, whereas at pH 8, the peptide will contain no ion pairs. So we need to use this information to figure out what the identity of residue 4 is, which kind of gives you a hint as to one of the ambiguous proteins. So we narrowed down that there were 2 options for residue 4 just based on like what its structure, and that would be glutamic acid or glutamine. And next in the question, we kind of want to look at residues 2, 6, and 8, because these are all the hydrophilic residues that have the possibility of forming an ion pair. So it would either be like 2 and 4 form 1, 4 and 6, or 6 and 8. And so those are the structures of glutamine and glutamic acid. You can see it's negatively charged. And so from this point, you should try out different combinations of potential amino acids to see what happens with these combinations. And so this is like kind of like a guess and check. But you already know what, you should have already determined what 2 is arginine, I think, and then 8 histidine. And so those ones you don't need to really alter that much. And it's important to pay attention to pKa and protonation states. If you do this, you'll find that there's only one possible combination that meets the criteria. And yeah, and remember that we know that amino acid 2 is arginine and amino acid 8 is histidine. And that amino acids will only be considered to ion pair with amino acids that are like directly next to them in the sheet. Question 5 is saying that another strand in the protein, not shown here, places the N-terminal end of an alpha helix close to the histidine residue. Will the pK value of the histidine side chain increase or decrease? And to explain your answer. So the key to this question is remembering that an alpha helix will kind of behave like an electrostatic dipole. So the peptide linkages are all arranged in parallel to the helical axis. So the individual dipole moments of all of the peptides will reinforce each other. And this ultimately leads to a positive pole at the N-terminus. So kind of a positive environment, will a pKa be higher or lower? And another thing to consider is that a lower pKa, well, pKa is a measure of acid strength. So a lower pKa would indicate that it's more difficult to protonate, and a higher pKa would indicate that it is easier to protonate. And so in a positively charged environment, will histidine be easier to protonate or will it be harder to protonate? And then that should give you your answer. And then other questions. Sorry, I didn't see a question until now, but what, in question 3, the beta sheet prefer to be parallel. Why is that? What exactly are you asking?
It's about question 3, actually. It's about question 5. Is the beta sheet gonna be it's gonna be parallel now? I did not get it clearly.
Roshan, do you want to answer that one since it's about question 3?
Can. Is it about question 3 on the problem set or the third portion of question 5?
Just the question 3 on the problem set.
Oh yeah, sorry. What was your question? There was some noise in my apartment, so I couldn't hear.
I just don't get it why it is parallel.
For which part? Oh wait, I know which parts. Sorry. Yeah. So let me try to explain this logically. So if it was anti-parallel, then basically what you're doing is you're flipping the sequence and then lining it up, right? So then in that case, the sequence would look something like IQQ, IIQ, and then NI. And then you can see there's like 2 interactions between N and Q in that setting. So the exact reason why N and Q don't interact very well is because N is actually shorter than Q. Q is like a really long side chain. So the hydrogen bonding groups wouldn't be like lined up properly for that to be as stable as the parallel configuration.
But but anti-parallel beta sheet is more stable. If not considering that N and Q itself, it's beta anti-parallel is more stable, right? Because
yeah, sorry, continue.
I mean,
no, that's not true. There's no difference in stability between anti-parallel and parallel. It completely depends on the sequence.
I mean, that's will there be repulsions of C terminals and N terminals?
No.
Okay.
No, because there's no carboxyl group and amino group anywhere except at the very end of the chain. So there's always a loop or an alpha helix or some structural element connecting 2 strands. There's only
okay.
1 amino group and 1 carboxyl group in the whole protein at the end of the chain. I think you're getting confused because the drawing just shows a beta strand, but it's the beta strands are either part of the same protein, or if it's forming an amyloid plaque, it's part of a much larger protein. So it's only showing you that short little beta strand, but you have to imagine that the chain goes to the left and to the right doing something else.
Okay, I can understand.
Hi, can I ask another question on question 3?
Yeah,
so
sure.
when I started this problem, I thought that we had to consider the possibility like that one beta strand could be offset by like a certain number of amino acids. Like, how do we know that they line up exactly and one side is not offset by some number of amino acids?
I think you might be overthinking it. I guess it could be offset, but the question just asks you to draw 3 asparagine side chains involved in a hydrogen bonding network. So I mean, as long as your final answer has them, I guess, interacting all 3 together, it should be fine, even if you, I guess, offset it somehow.
Oh, sorry. I mean, for part 2.
Oh, okay.
Yeah, like the INQI QQI
Oh, okay,
sequence.
Sure.
Like, how do we know that I lines up with, in the parallel conformation, how do we know that I lines up with I and lines up with N instead of maybe one strand having I and Q, and then the other one maybe starting with Q and then being QII, and like QII lining up with I
like
and Q,
it starts
you know what I
somewhere
mean?
in the middle of the sequence.
Yeah.
I guess it doesn't say that explicitly, but the way I saw it, there were like, what is that? 8 bubbles and 8 amino acids. So it felt like you had to fill in one, like it was a 1-to-1 correspondence. But yeah.
Okay. All right. That's okay. Sure. Thank you.
Yeah. Sorry, I couldn't, I guess, explain that more. Yeah.
Sorry, what was your could I ask just one thing about this question as well?
Oh yeah, absolutely.
Yeah, I was wondering, so what was your reasoning that N and Q interaction is not favorable?
Oh, so N is much like smaller, like the side chain itself is much smaller. So if they're like, if N and Q are next to each other, then like the hydrogen bonds will be kind of far apart, and it'll not, I guess, be in position properly for a strong interaction, as opposed to if you have like the 2 long ones line up, then they'll be closer to each other and are able to interact strongly together, and the 2 short ones together.
Oh, okay.
Yeah.
So you're saying the 2 short ones would interact better and 2 long ones would interact better, but if one is short and the other is long, then it wouldn't interact.
Yeah.
Well.
So for this specific question, if you look at the position of the N and the Q, in the parallel configuration, both the N's are at the bottom. So you can imagine kind of it's not like, they're not like, there's sort of like a rotation on the, I don't know what axis that is, but on the axis of the amino, of the peptide chain, so that the short ones can kind of like stick together and the long ones can kind of jut out a little bit, and they interact better like that.
Okay.
I will stop the recording, but if you have any more questions, continue to ask.